welcome back to Cody's Lab. It's been a while since I've done a chemistry video, so here's one that's been on my list for a long time. Back when I first learned about this, it totally blew my mind, so let's see what it does to yours. Okay, so here's the setup. I have two test tubes. They're each filled with saturated solutions of an ionic solid. In this case, I have some ammonium sulfate, which is a common fertilizer, especially in areas with alkaline soil, and good old sodium chloride, table salt. Now I've produced these test tubes by taking the respective salts, putting them into a beaker, adding some water, putting them into a pan on the stove to heat them up to dissolve as much of the salt as I could. And then while the solution was still hot, I pipetted some out into these test tubes and let it cool. As it cooled, the solution, water, could no longer hold as much dissolved solids, and so some of it settled out. So I'm left with test tubes with a saturated solution and a small amount of salt left over. Or in the case of the ammonium sulfate, a rather large volume of salt. It's fairly low density, so I should be able to break it up. Might have to get a wire and bust that up. So now, what happens when I tip both of these together into this larger test tube here? Go ahead and make your predictions now. So, sodium chloride goes in first. There we are. There's my saturated salt solution with a little bit of extra salt. Now the ammonium sulfate, same thing. Just like that. Get as much of that salt in there as I can. I'm left with a test tube that looks like this. Now, watch as I shake them up. This might be easier to... There we go. Let's just rock it back and forth. I'll speed the video up later. Look at that. All of the salt has dissolved, leaving me with a clear solution. Isn't that wild? Two saturated solutions with extra salt, and it was able to dissolve all of it. So how is this possible? Did the solution heat up as the salts reacted? Well, these salts don't react together. And if I take a thermometer here, little infrared thermometer, you can see room temperature 29°C, over to the test tube 30°C, 29°C. So it did heat up a little bit, but it's probably just because I was handling it with my hands, body temperature being transferred. The solution did not heat up. There was no reaction that took place here. So what happened? So to explain, I've made a little salt crystal here using magnets. This is a model. It's not exact, of course, but there's a lot of similarities between a block of magnets and a salt crystal, or indeed most forms of matter. See, everything's made out of little particles, and many of these particles have a bit of a charge, and they like to stick together, just like magnets. In fact, what a magnet is just a piece of matter with a charge that doesn't cancel out over macroscopic scales. Not exactly, but you can think of it like that. So, salt particles like to stick together, and they like to arrange themselves in nice, neat patterns, forming crystals. Now, water also likes to form crystals. The crystals are a little bit different, but still the same thing. And just like anything else, heat it up, raise the temperature, the particles start to bounce around and come apart, and water at room temperature is a liquid, whereas salt is still a solid. In fact, you have to get it to quite high temperatures before it melts. So the water is liquid, and the particles are kind of moving around like this. Just kind of lots of random motion. They might have a little bit of attraction, right? But they've also got too much energy and they don't have the ability to stick, so they just come right apart as soon as they collide. Now, water also is attracted to the salt molecules. A single water molecule, it might collide with the salt crystal, give it a little bit of a tug, but it's not going to do much. You start getting a bunch of water molecules together. Eventually, the water molecules are pulling on the salt particle harder than the salt is being pulled on by the other ones, and it pulls it off, just like this. And those water keep attached to it and keep it suspended in the solution. And then that might happen again and again and again as the water dissolves the crystal. This whole thing is an equilibrium process. You see, if the salt particle happens to strike the crystal just right, it'll still stick on. It'll pull itself away from the water, say the water didn't have a good hold onto it and it was able to pull on and reattach to the crystal. And then of course the water might pull it back off. And there's a process here. Eventually, there's so many salt particles in solution that the odds of them going back on equal the odds of it being pulled off, or the rate that they're being pulled off is equal to the rate they're being put on, at which point the crystal stops dissolving and the solution is saturated. So what happens when you heat up the solution is everything gets more kinetic energy. The water molecules are moving faster, but the salt particles are also given more kinetic energy. So the salt crystal might still remain a salt crystal. It's not melted yet, but it's got some more motion. And it takes less energy to pop one off because it's already starting to kind of try to pull itself apart already. So it takes less work for the water to pull pieces off. So more of the salt particles are going to wind up in solution when the temperature is higher. In fact, really, if you think about it, what's going on is the combination of salt and water, it's really kind of melting the salt crystal. The water is just lowering the melting point. Dissolving is fairly similar to melting in a lot of ways. So now, what happens if I have two different salts? So here's a different type of magnet. These are round, these are square. Of course the square ones are still going to want to stick, but let's just say that the crystal structure is different and the square ones don't really want to go in and fit where the round ones would. They'll still have a little bit of attraction, but they're easily removed. So if I have a bit of the square salt, the square solute, and it comes in, it comes on, it might attract to it, but the water's easily going to just pull it right back off because it doesn't fit in perfectly. It doesn't want to snap into place. And so the water is doesn't have to do very much work to pull it away. And so the square does not really stay stuck to the round. See? And the opposite is true. The round ones don't want to stick into the holes where the square ones would fit. It's not the right crystal. It doesn't fit the right pattern. So the water is easily able to just yank it off. So what this means is the solubility of the round particles is not really affected by the presence of the square particles. It might change a little bit. The square might even aid in the solubility slightly. It starts to act as a solvent in its own right. But a lot of the times you can just ignore it. Let's say the solubility of round is 10%, so 100 grams per liter. By adding another liter containing dissolved square particles, well, square particles are ignorable. So really I just added another liter of water, so I've increased the amount of space that the round particles can be dissolved in, And so now the solution can in total dissolve 200 grams of the round one, along with the amount that it had dissolved of the square, plus if the square had, say, 200 grams per liter solubility, now the whole solution together could dissolve 400 grams of the square. This brings my total, 400 grams of square, 200 grams of round, to 600 grams of total dissolved solids in the 2 liters, or 300 grams of dissolved solids per liter, which is still more than either of them on their own. And in fact, if you measured the density of this solution, you would find that because of the dissolved salts, the density is higher than it would be for either of the dissolved salts on their own. There's more stuff in here. In fact, I took advantage of this in a previous video. Circe solutions, the salt water that's dense enough to float rock, and mix together malonate and formate salts of thallium to produce a very heavy salt saturated water solution. In fact, so dense that it could float diamond. Another application of this is, say you're making taffy or some other candy, and you start with sucrose. So sucrose is kind of like glucose and fructose bound together. So you got a bunch of these units which form crystal structure of their own. But if you break them apart by adding some sort of acid, vinegar, cream of tartar, etc., break them apart, now you can have more sugar, in total amount, dissolved in a given amount of water, so that you are less likely to form crystals and you make better candy. You don't want crystally taffy, otherwise it would be not so good. But the area where I've been able to apply this knowledge most often is for purifying substances. Say I've got some of the square, I think we said, say it had 200 grams per liter of solubility, and some round mixed in with it as a contamination. It has 100 grams per liter of solubility. But there's way more of the square. So, as you start evaporating the water, the square starts coming together as the total amount of it per liter reaches the 200 grams per liter. But the round ones, there's much less of it, so you don't reach the 100 gram solubility limit until there's much less water and most of the square substance has already crystallized out of solution. So it'll be crystallized, whereas the round will still be dissolved. That leaves you with a pure crystal that doesn't contain the round. So this is purification by crystallization. And it doesn't have to be water, it could be some other solvent. And it doesn't have to be salts either. But there are a few caveats. There are some things that won't work. So to show what I mean, I'm going to take my original solution here with the ammonium sulfate and sodium chloride. I'm going to transfer it into 3 more test tubes here. Split it up just like that. Now this first one over here, I'm just going to add some potassium nitrate. So this is a different salt. We should expect to see this one not interact in any way, so it should just dissolve. So give that a mix. Okay, so there's most of the potassium nitrate dissolved into the solution. So now the solution's got ammonium sulfate, sodium chloride, and potassium nitrate all dissolved in there. So I've made a very dense solution here. And that's exactly what you would expect from the information I gave previously. But now, instead of potassium nitrate, let's use calcium nitrate. So it's very similar. It's just calcium instead of potassium. Let's make a solution of it. So add my calcium nitrate into a little test tube full of water. You'll find calcium nitrate dissolves quite easily. It's highly soluble in water. Now, if I tip it over into my solution with the ammonium sulfate and sodium chloride. Give that a mix. Just let it sit there for a few minutes and watch what happens. Let's get those bubbles dislodged there. There we go. You notice already the solution is becoming quite cloudy. What's going on is we formed calcium sulfate, which has a very low solubility in water, and so it's precipitating out a solution. See, what happened is the calcium ions and the sulfate ions, they bond together very strongly. So it's like very strong magnets. When they find each other, they're very hard to pull apart. So the water is able to only pull a few of them apart, so the solubility is very low. In fact, so low that adding just a little bit of the calcium to solution resulted in the calcium finding the sulfate and dropping down, leaving ammonium nitrate and the sodium chloride behind. Okay, so this could be useful if you have something that you know will react to form something very insoluble. So if you have some silver nitrate and copper nitrate in solution, add a little bit of a chloride salt to it. The silver and the chloride will find each other and that forms something that's very insoluble. The copper chloride is still fairly soluble, so the silver will fall out of solution, leaving the copper behind. So it would be a method of purifying that way, which is great if you're wanting that, but if you're not wanting that, well, it's good to know that could happen. So in this final test tube, I'm going to add a small amount of a hydrogen chloride solution. So this is basically a very strong source of chloride ions. This is hydrochloric acid, by the way. So if I'll add this in, watch what happens. Because that we get a precipitate forming immediately. And that'll snow out. I think it looks rather pretty. So what happened there is the sodium chloride, it's sodium and chloride, those come apart in water. You have sodium ions and chloride ions. Now of course the sodium bonds to chlorine in an organized pattern which forms the crystal. Now if I have a whole bunch of chlorine in solution, the chlorine is not just going to all bind together like that. No, it needs to bind chlorine to sodium, chlorine to sodium. So you got a whole bunch of chlorine in solution. As soon as you have a sodium exposed, the chlorine is going to bind to that very quickly, because there's a whole bunch of chlorine ready to go. And now you've got the chlorine there. Well, of course, the sodium is going to be the next to bind together. It might take a little bit longer, but it's more likely now that the chlorine's sitting there. So sodium bonds in. As soon as the sodium hits, and the chlorine is going to find it immediately. So that increases the rate that the crystal forms, decreasing the overall solubility of this particular salt, causing my sodium chloride to fall out of solution. Now there's also ammonium ions here. Ammonium ions do also form a chloride salt, which might precipitate if you added a whole bunch of chloride ions, but sodium chloride is much less soluble, and so these are going to fall out first. For those of you who are more mathematically minded, let me see if I can explain this a little bit better. Okay, got the required mathematical protection here. So the dissolution equilibrium reaction is going to look like this. So the solid is going to be dissolving with an equilibrium into X and Y. Like this. So maybe X plus ions and Y minus ions. These are of course aqueous. Just going to scribble there. Just like that. So now this equilibrium reaction has a solubility constant. This reaction constant is the solubility product, which I'm going to just write as P, which equals the concentration of the x plus multiplied by the y minus here. Don't worry about the signs here, it doesn't really matter. So this is the product, which is a constant at a given temperature for the saturated solution, what is dissolved. And the smaller this number is, well, the more solid we're going to end up with. The bigger this number is, the more solutes we're going to end up with. If the substance breaks apart into 3 pieces, well, then you just add in another thing here, making C. If you have something that breaks apart into 1 positive ion and 2 minus ions, it just ends up with 2 y's multiplied together, or y squared. So with our sodium chloride example, we've got sodium chloride, which breaks apart with the equilibrium reaction into sodium plus dissolved plus chlorine minus dissolved. The product of this is going to be equal to the sodium concentration times the chlorine concentration. Okay? Now what happens if I add a whole bunch more chlorine? We raise this up. Well, it's going to make this number bigger. And that's a problem because this is a constant. So if this number is wanting to get bigger, if we add a bunch of this, basically what's going to happen is this one's going to have to go down to compensate. So in order for this one to go down, the sodium and chlorine have to find each other and form a solid, so it's no longer part of the equilibrium reaction. So this reaction shifts towards more sodium chloride being formed as a solid. And the opposite would be true. If you remove one of the ions, take it out, then the equilibrium would shift and the solid would dissolve. To sum up, if you add together 2 different types of salt, the solubility of the 2 will be completely independent, and so they'll both dissolve into the solution. Unless you have the salts which have similar ions, the salts find each other to form something even less soluble, or you're not working with salts and the substance you added actually acts as a solvent, or something that your substance doesn't want to dissolve in. Suppose I should demonstrate that, huh? So let's take my solution here and I add a little bit of ethyl alcohol. Watch what happens. Yeah. I end up with a bunch of salt precipitating out of solution because... So what I've done here is I've added a bunch of a solvent that can't dissolve the salts, and by doing so I've spread out the solvent that can dissolve the salts, so less of the water molecules can act on any given salt particle, and so they're less likely to be able to pull the crystals apart. So crystals form, precipitation occurs. Anyway, I hope my ramblings made sense and was enjoyable, and I'll see you next time.